Oil and gas prices have been yo-yoing for weeks. A major reason is the tension surrounding the Strait of Hormuz, a narrow 39-kilometer passage that handles nearly 20% of global oil supplies. That geopolitical volatility has pushed Europe to aggressively accelerate its rollout of green technology. To physically build their way out of fossil fuel reliance, consumers and governments are scrambling to purchase electric vehicles, heat pumps, and plug-in solar systems. Economically, the shift is working. Harnessing sunlight for energy saved the European continent over 3 billion euros in March alone. But there is a massive operational hurdle to this transition. Unlike coal or gas plants, renewable energy sources are entirely dependent on specific environmental conditions to function. As global temperatures rise, we are seeing more intense heat waves, heavier rainfall, and rapid shifts in weather patterns. The climate change that solar and wind farms are built to prevent is now directly testing their physical limits. Take solar power. You would logically assume that hotter, sunnier days naturally lead to more electricity. But solar panels actually have strict thermal limits, and intense heat rapidly degrades their efficiency. As a solar panel's surface temperature hits 65 degrees Celsius, its capacity drops by 20%. This happens at the worst moment. Extreme heat spikes air condition demand, creating a massive electricity need exactly when the solar grid underperforms. Wind energy has its own physical boundaries. Blustery conditions are excellent on paper, and they recently helped the UK break renewable records, generating enough wind power to supply roughly 23 million homes. But turbines have a precise mechanical sweet spot. When wind speeds exceed 90 kilometers per hour, the machines enter a survivability mode. They literally feather their blades to a complete stop to avoid structural failure. Even when they operate perfectly during high winds, they can produce too much power too quickly. This creates rush hour traffic on the grid. The electricity gets trapped in the system and cannot be routed to the places that actually need it. The result is a process known as curtailment. Grid operators are forced to intentionally turn off the spinning wind turbines and pay gas plants to switch on and stabilize the system. Last year, this bottleneck cost Britain nearly 1.78 billion euros. Water presents an entirely different challenge. Norway is heavily relied upon as Europe's biggest battery, with thousands of dams providing a stable supply of hydropower. Hydropower relies deeply on snowpack. While rain creates immediate, sudden runoff, snow acts like a physical storage mechanism. It holds water through the winter and releases it gradually during the spring and summer for a highly predictable flow of electricity. However, warmer winters are breaking that cycle. Because the atmosphere holds roughly 7% more moisture for every 1 degree Celsius rise in air temperature, winter precipitation that used to fall as snow is increasingly coming down as intense rain. This chart compares Norway's historical winter snowpack to current levels. Following a remarkably warm winter, snow reserves plunged to a 2-decade low. That missing volume created a 25 terawatt-hour deficit, enough to power 2.5 million homes for a year. What was once a highly reliable baseline power source is becoming highly volatile due to shifting weather patterns. Whether it is a solar farm, a wind turbine, or a hydroelectric dam, all of this energy ultimately runs into a single piece of aging infrastructure, the electrical grid itself. Right now, more than 120 gigawatts of planned green energy projects are at risk of stalling. According to recent data, half of all grid operators simply do not have the physical capacity to connect these new power sources. For the past decade, industrialized nations heavily subsidized and built clean generation technology, but largely neglected the transmission arteries required to actually move that power. Fixing this vulnerability requires massive structural engineering. In regions prone to extreme weather, operators are deploying specialized typhoon-resistant offshore turbines, engineered specifically to survive wind speeds up to 215 kilometers per hour. The software and the systems are adapting alongside the hardware. Grid operators are implementing AI-driven forecasting models to predict chaotic hydropower output, and the European Commission recently unveiled a 1.2 trillion euro effort to overhaul its network of wires and substations. Erecting a solar panel or anchoring a wind turbine is merely the starting line. To build an energy system capable of withstanding the climate extremes it is trying to prevent, we must weatherproof the infrastructure connecting it all together.